He completed his PhD at Princeton University. Are we recording it? Yeah. So Tom's environmental economist who completed focused his work on impacts of climate change. He completed his PhD at Princeton University in December 2025. He is now a postdoctoral research fellow at the University of Exeter and a visiting fellow at the LSE Grantham Institute. Today, Tom is going to be speaking on the carbon at risk measure can unlock financial markets for large-scale carbon removal.
Got it. Okay, great. Nice to meet you all. Super interesting to hear about everyone's work. I'm used to economics seminars in which everybody interrupts all the time. So
Me too.
Okay, good. So don't feel like you have to wait until the end. Most plausible pathways to net zero require large-scale carbon removals by 2050, which is quite soon. So currently, we're removing about 2 gigatons of carbon dioxide from the atmosphere, and we need to scale that up to between 7 and 9 gigatons removals by 2050 in most sustainable IPCC scenarios. And to do that, if we're going to do that, we're going to need to spend a lot of money. So kind of plausible estimates say that achieving that type of level of carbon removals costs trillions of dollars. And in a context where we need a lot of capital investment, clearly there's a lot of market actors, regulators, buyers, insurers, investors, who will want to know how to allocate their capital into a portfolio of projects that have different risks, different impacts. And why do they want to do that? Well, the reason is there's risk associated with any project. It's something I think a lot of you work on, so it won't be news. But obviously, some forests burn, some storage contracted leaks, and understanding and managing that is critical for stakeholders and for creating, for achieving those carbon removal goals. So there's, like the market actors that are going to care about this, regulators, a lot of them, especially in Europe, not so much in America, as we're discussing, they might want to set buffer requirements such that if you, contract some removals, you actually over-contract such that in the case that when the project fails, you still meet the targets with some possibility. And buyers with corporate net zero commitments want to make sure that they reach those commitments under a broad range of possible outcomes, for example. And there's also like a large insurance market. So I should probably give a bit of background to this project. This project started, I did not start this project. This project started as a group of private sector and academics coming together to a series of meetings where they're trying to think about what would it take for an insurance industry to develop around carbon credit markets. And this is kind of the outcome for this that kind of discussion. But basically, unless insurers can understand the different risks associated with different types of carbon credits, they're unlikely to be able to enter the market. So what's the current way that carbon removals and credits are kind of categorized? There's no standardized risk metric, and investments are often guided by qualitative labels, such as this is a permanent removal, such as something like a geological storage, whereas another is a non-permanence removal. For example, some kind of nature-based solutions are often branded as being non-permanent. And other qualitative labels are just by the type of project, so like nature-based or engineered. And as I've kind of been saying, there's a broad range of consequences that kind of flow from having a market where there's not a good understanding of risk. So there's kind of issues with moral hazard, missing insurance markets, and there's difficulty in creating diversification strategies that would allow you to hedge against bad outcomes for the climate. So the point of this paper is to propose a standardized metric that would allow you to communicate the anticipated performance of carbon removal approaches. And there's kind of two kind of key ideas here. We want to be able to provide a common language for these different market actors to be able to compare projects on any kind of scale, on the same scale. And it's important for this purpose that the metric is kind of technology agnostic. We're not actually concerned here with the specific origins of a given removal. We're concerned with the risk of undelivery for a given portfolio of those projects. So, when you're thinking about designing, what should this metric look like? Well, obviously, if possible, you don't want to start inventing the wheel if someone's made it before. And so the kind of approach was, well, up into the 60s, 70s, 80s, financial markets faced the same kinds of issues when they were trying to compare portfolios that have different risk structures. And the kind of metric that many different actors converged on was this idea of value at risk. And the value at risk provides a common measure of potential loss at a given horizon and confidence level. And it's been widely adopted by regulators across the world and insurers, investors, buyers as a relevant measure of risk. So what's the definition of the value at risk? Well, it's just the maximum potential loss in the value of a portfolio due to bad market outcomes for a given probability. Just can think, in maths, it's just kind of like a quantile of the possible loss.
Why is it the maximum? Because maxima are notoriously hard to predict rather than 90th percentile.
So, I mean, it is just this percentile here. So if you think about, let's say that we currently have a portfolio and we're thinking about how much will it lose by next week, then the value at risk is just the kind of the difference between, what it's worth now and the 10th percentile, the 5th percentile, or the 2nd percentile. So the value at risk here is this distance.
But you said maximum.
Yeah, so it's the in this I guess it's we're not looking at the kind of integral under the tail here. That's a different concept. That's like an expected shortfall based approach. Some people do use that. So you're right, this doesn't capture the tail risk, right? This is just saying at the 90th percentile, what's the kind of best case scenario in that case? It's not saying what's the conditional on event happening that's bad. It's not saying how bad is that event.
So you're predicting the 98th percentile value.
Yeah.
Yeah. I see. I think that's just the maximum, but you call that the maximum, but actually it's not the maximum, it's actually 90th percentile value. By maximum you mean that, you know what I mean? It's not the maximum loss of the probability. The definition seems incorrect to me. It's saying that the probability of the loss.
So I think the VAR, right, is going to be defined as, if you just think about what's the value here, it's the maximum value.
The loss exceeds this value.
Exactly. So what I'm kind of saying here is like, you're right that this is a limited measure because it doesn't tell you something about how fat.
I think the word maximum is correct. It shouldn't be there. It's just a loss less than this. You can't use the word maximum there.
That's helpful feedback. Thank you.
Yeah, because in our work on permanence, we use the same metric. We call it exactly. We don't say maximum. It's just say the probability that the loss exceeds this particular value is upper bounded by a certain value.
Okay, yeah, that's helpful feedback.
Yeah.
There's obviously a tension between using the language that people use in the finance.
Yeah, the finance industry that they were notoriously bad in its mathematics.
Okay.
At the very end of 2008, they have no idea what they're doing.
Yeah, that's me. They'll come out on that. Anyway, this is whether the specifics of the definition. Hopefully, it's kind of clear what this is getting at, right?
Yeah.
The financial markets. This is if you look in any financial portfolio analysis, you'll see VAR all over it. And this is just meant to say something about the modeled kind of worst case scenario type thing at a 90th percentile. But I think your comment as well, so this was a discussion about the definition, but it's also a limitation of this measure, I guess. There is that this is just looking at that percentile. It's not looking, there's two ways, there's a lot of distributions that are consistent with the same 90th percentile VAR, right? How fat the tail is, it's kind of not affected by.
That's right. I mean, you could have very, very large losses. That's exactly. The probability of that loss is less than 90%, 10%.
Yeah. And there are some people that argue that focusing on this type of measure is not good because it's really the very, very bad tail events that drive things like financial crises.
Yeah, I mean, because, I'm sorry to jump into this. There's this whole line of work which takes a different approach altogether, and that takes the amount of risk multiplied by the amount of loss and multiplies the two together, and says if you have a rare event that has a very big probability that you should pay attention to, if you look
that's the expected shortfall, I think.
It's not an expected shortfall. This is how it's done for cybersecurity and anti-terrorism kind of stuff. So there's a book called 5 Times Faster than Simon Schott.
Okay.
And he said the reason why economists get things wrong, and it's because they are looking mostly at median measures. Mm-hmm. And what you really want to do is there's a 1% chance of having a heat wave when you kill 1 million people, where it has huge cost. That is actually a very big thing because even though the probability is low, the associated cost is so high that it's worth paying attention to. Whereas you say, well, that's less than my VAR, Yeah,
Absolutely, yeah. There's a big literature on this in economics as well, especially by Martin Weitzman. Where it's like tail risk dominates any cost benefit analysis.
Right. This is the black swan approach.
Yeah. I'm not going to get into that.
Okay.
Leave that to someone else. We're looking at the value at risk.
Okay, got it.
So I told you about the value at risk that people are using in finance. We want to translate those ideas into the carbon market and see if that can be helpful for our goal, right, which is to have this common language for different people to talk to each other. So this definition, I'm going to tweak this the maximum, but you get the idea, right? So we've got this VAA concept that's used in financial markets. We want to adapt this to carbon markets. I'm going to change some of the language. So rather than talking about loss in value, we'll talk about the shortfall in carbon removal. Rather than talking about a financial portfolio, we'll talk about a removal portfolio. Maybe I've got some biochar, maybe I've got some DACCS, maybe I've got some forests, some nature-based solutions. And rather than what market movements, we'll just talk generically about project performance. And that could be a function of all kinds of things like political risk. It could be about fires. It could be about climate change. It could be whatever. So the carbon at risk is just defined as the maximum potential shortfall in carbon removals of a removal portfolio due to adverse project performance for a given probability. So exactly the same definition. And just the definition of what that is. If let's say that I've been contracted to remove Q tons of carbon, but in reality, there's some random variable D which defines exactly what's going to happen. Let's say that we know the CDF for D somehow. Then the carbon at risk is kind of Q minus the 5th percentile, the 95th percentile carbon at risk. To kind of visualize that, let's say that I've been contracted Q here, and somehow I know the CDF for the actual delivered carbon, the carbon that will actually be delivered in 100 years' time. Then there's some risk associated with that. So the expected removals is not exactly the amount of removals that we've been contracted. And I've just kind of labeled the quantiles here as well, the fifth,
The PDF, not the CDF.
So
this is the PDF. This is the PDF, not the CDF.
This is the PDF. Yeah. I guess if you know the CDF, you know the PDF.
Right.
You're right. This is the PDF. And then the carbon, the 90 percentile carbon at risk is just the difference between the contracted removals and the kind of worst 10% of the outcomes, the maximum of the worst 10% of the outcomes. And obviously, analogously, the 95th percentile, 98th percentile. Importantly, you can decompose the carbon at risk into kind of two components. There's like a systematic shortfall, which we would expect to happen, and then there's a tail risk component as well. Now, the interpretation that I've just given you is this kind of risk framing, it's maximum shortfall at 95% confidence. But there's immediately a second interpretation that you can give the carbon at risk, and that's the extra tons that are required to remove a particular level with 95% confidence. And just to kind of illustrate that, like imagine that I want to deliver Q star with 95% confidence. How much should I buy? Well, in reality, if I buy Q star, some projects will fail. The carbon at risk is just exactly the amount that I need to buy on top of Q star in order to make sure that I will deliver Q star with 95% confidence. So that's why this is a very useful metric for kind of regulators and people that want to buy, corporate investors who want to buy with a certain level of confidence. So one more concept before we get into the kind of paper, I guess. We use the carbon at risk to define a concept that we call the risk-adjusted cost. So if you just look at the sticker price or the price per contracted ton of two different projects with totally different risk profiles, you'll usually find that the riskier project is cheaper. Not always, but usually. But if the risky project has a lot of carbon at risk, then you need to buy a lot more tons in order to guarantee delivery of a given confidence level. And therefore, we define this concept called the risk-adjusted cost, which just accounts for that fact. So discounts risky projects in order to kind of give a likely apples-to-apples comparison for delivery at a given confidence level. So just kind of an example of how that might work. So let's say I'm comparing two projects, a DACCS project and a forest project. One is 10 times more expensive than the other in terms of the sticker price. But when we look at the cost, the effective price, which is just the cost for achieving this 95%, the delivery of 95% confidence, then there's only a 5 times difference. So it can obviously materially affect what I would choose to buy. So the kind of contribution of this paper, this is not obviously the first paper that's looked at risk in conservation type analyses. There's these nice papers that do kind of Markovitz mean variance optimization. for reforestation and conservation under uncertainty about how much climate change we're going to have. There's an idea called a climate VAR, which is sometimes used in finance. That's not really what we're doing, it just sounds very similar. The climate VAR is when people have tried to work out how much of their value that they have in their company is at risk from climate change. So it's just a completely different concept, just happens to sound very similar. There's a lot of papers, and I've just picked one here because I think it's a really nice one, but there's a lot of papers that have shown that existing buffer pools for carbon credits just are severely undercapitalized. So, for example, the Vera and the gold standard, which are kind of project registries for carbon credits, they do recognize that projects have risk, and they say, look, we're going to have some kind of buffer pool. But in general, they have a very small buffer pool, and it's at a flat rate per project. So it just says we're going to buy 20% extra carbon credits of whatever it is. That's clearly wrong, right? If different types of projects or portfolios have vastly different risk profiles, and it could lead to inefficient investment in capital allocation. So this is a nice paper here that just talks about California has a buffer pool, and it's just undercapitalized by a factor of about 50 or something. So and there's also some papers, including, I think this is maybe the paper that you were involved in a few years ago, that kind of talk about the welfare economics of temporary storage, how it's priced for impermanent removals.
The social price, yeah.
Yeah, the social price. And there's a really nice paper as well by, I think these people are at Oxford, and they've kind of thought about buffer pool, how to construct a buffer pool that allows you to meet a particular set of carbon targets with a certain probability. So a very related concept as well. So some disclaimers. This carbon risk is meant to be an evolving kind of idea that different private sector and public sector actors can take on. It's meant to be recalibrated as data and science improve. It's kind of aimed to focus on delivery and storage risk. It's not yet for thinking about additionality. So I don't know if people are familiar with the concept of additionality. Just the idea that a project is additional if it would have only happened with the carbon credit that was bought. So it's not additional if it would have happened anyway, right? And it turns out a lot of projects have really struggled to show their additionality. And this carbon at risk concept is obviously not a complete solution. It's going to be a conceptual foundation proof of concept. Now, clearly, what's the problem here? And this all seems kind of straightforward. Well, the difficult thing is if you want to operationalize the carbon risk, you have to be able to somehow estimate that CDF, right? And that could be challenging because you need to kind of get this full distribution of potential removals at a future date. There's kind of broadly speaking two strategies for how you might want to do that. If you're in a data-rich environment, then maybe you'll think about calibrating this CDF using real-world data, right? Look at what's happened in the past and try to use that to project the future. Maybe making some adjustments for climate change or technology changes, something like that. But there's also a bunch of situations which we really care about where we don't have any data whatsoever, right? Maybe we're thinking about carbon credit for a novel technology, for example. And in those cases, we're going to have to use models, right? We cannot use empirical data. So in this paper, what we're going to do is show an example of calculating a carbon at risk using both a data-rich environment and a data-poor environment, just to show that at least can be done and to kind of give a kind of proof of concept that other people can hopefully improve upon. Okay, so roadmap for rest of the talk. We're going to show a forest, an example of an empirically calibrated car construction for a forest example, a model-based car construction for a DACCS example, and kind of talk about portfolio theory, how to combine optimal combinations of projects, and then just the governance and policy implications. Any comments or questions are very welcome at any point. Okay, so forest example. So obviously forest is something a lot of people are working in this. There's lots of reasons why a forest project might fail, from disease, harvesting, rights, all this kind of stuff. In this example, we're just going to focus on two really key fundamentals, the fire risk and the propensity to regrow. We're going to look at three regions across the world with different fire risks and different propensities to regrow. And what we're going to do is kind of do a simulation to try and get an empirical understanding of what the future CDF might look like. The way that we do that is that we use fire history data for each of these different regions from a satellite-based product. And we, for parcels of land in these different regions, we kind of conduct a simulation where we sample from the historical distribution of fires for a given parcel. and we kind of update, over time as it gets in each period gets a chance of being burned, and then gets a chance to regrow. And we kind of run this through time many, many times, and we can calculate quantiles across that distribution of possible scenarios.
I mean, one thing we found with this kind of thing is that fires are actually quite rare. I mean, if you look at most of the time, the probability of fire is like 0.01%.
Absolutely, yeah, it's a really important point.
So we hear about large scale fires because they are, they're so rare actually. So I mean, we struggle to predict fires. And when you do have fires, predicting that there will be a fire in California is relatively easy, but predicting where the fire is going to be is very, very hard.
Yeah,
right.
Sure.
So when you talk about a forest project,
Yeah.
that's in a limited region of interest.
Yeah.
In that region, to predict that there's going to be a fire, there has a certain probability of a fire, is even with the so-called rich data, it's actually not that easy because it depends so much, right, on so many different factors.
Absolutely. Like the historical record that we're using has 22 years in it, right? So fitting something with a flat tail to that is essentially impossible.
Exactly.
Right?
Yeah.
What we do is we kind of we first use like the empirical CDF of past fires and just look at what happens then. But you're absolutely right? That doesn't include the really bad tail.
Yeah.
Right, that's 22 years of data.
Yeah.
So we also take a second approach where we kind of fit a model which has a very long tail, like a generalized Pareto distribution, that allows us to at least examine what happens when we allow for that tail. And when we run forward for like 50 years or 30 years, obviously those tail outcomes really matter. Right?
Yeah.
So
I mean, and factoring in climate change and warming in atmosphere and higher fire risk, that becomes challenging.
We do factor in climate change. Like we update the probabilities of burning according to some climate drift parameter that we've pulled from the literature somehow. Right. But obviously it's not perfect. Yeah. But it's still, I guess the point here is not to say this is exactly right, but what we're trying to say is this is better than not doing it, right? Which is what people are doing right now when they're pricing their carbon credits. So let's start by analyzing. Yeah, and I guess this is also related to your point as well, I think. When we look at different projects, and let's say we're looking at like 100 different projects, all in California, what's going to be a really crucial factor is what we assume about the correlation between the probability of fires in different places, right? And that's, I think, your point about locations.
Yeah.
Let's start by just saying that we're looking at a single project in a representative grid cell in California. Or we can think about this independent project. So California is made up of a bunch of different islands, right, with water around them. Obviously, it's nonsense, but it's a good starting point. So we can now just plot the kind of carbon at risk as a function of time for a portfolio with a single project in it. And this is the carbon at risk per ton for these three different regions: California, Mato Grosso, and the carbon at risk for California kind of really increases quickly over time and then kind of stabilizes where it's increasing due to climate change, basically. The differences, the kind of cross-sectional differences between these three lines are entirely driven by differences in the regrowth rate compared to the differences between the burn rates. So California has relatively high burn rates and relatively low regrowth rates, while as the other two regions have like more of a difference between their regrowth rate and their burn rates. So this was for a single project. What if we instead had hundreds of projects or 20 projects or whatever? Let's continue first with this assumption that these projects somehow have independent fire risk. Then we have the lovely central limit theorem kind of stuff kicking in, and basically tail risk disappears, and because the distribution collapses on its mean. And that's great news. It's basically saying you get a free lunch, right? You get more projects, just gives you less risk. Great. And economists obviously like to say that's not possible. They're right here because this is a nonsense calibration. And this is just to kind of illustrate that. Here's the carbon risk from this orange one just reproduces the previous line for California. And as you increase the number of projects, actually the carbon risk just kind of collapses onto the mean because the whole distribution kind of shifts down. Now let's try and introduce dependence, right? So in the previous analysis, we were just assuming that it's possible to somehow have independent projects in the same region. But in reality, a very hot year, right, increases the fire risk for everyone in the same place, or a year with very bad political regime or whatever it is. So the kind of simplest way to think about this is just to allow for like pairwise correlation between projects. And under pairwise correlation between projects, the variance of a portfolio is no longer just this like nice simple object. It also depends on that covariance parameter. And you can kind of think of this obviously nests the previous case. Under independence, we get back to the nice simple case. Under perfect correlation, there's absolutely no benefit from having more projects, right? If every project has exactly the same risk in every single year, more projects doesn't reduce your risk at all. The carbon risk stays exactly the same. But in this kind of intermediate case, which is the real world case, then there are some benefits to diversification, but not as much as if the projects were independent. So how much diversification is?
I think you're also making the assumption that the project sizes are similar.
So
the project sizes are similar.
Yes. Yeah.
But that may not be the case.
That's a very interesting point. Yeah. I think we are. Great point, actually. I need to think about that. Yeah. Yeah. So one thing that we did is just look at the empirical correlations between the probability of one grid cell having a fire on another as a function of distance. There's like a relatively steep decay in this function. Like once you get to about 400 or 500 kilometers away, then there's actually relatively low correlation between grid cells.
Sorry to jump in again, but then you should be doing a semi-radiogram here. Yeah, because that will give you the spatial correlation distance rather than the scale.
Yeah, that's a fair point. Yeah. Absolutely. Thank you for that. That's a great idea. This assumes a lot, obviously. This assumes all kinds of things. I think the worst thing that it assumes is really that this is 22 years of observations. That means it's hard to capture really proper tail risk, or it's impossible to capture proper tail risk. And it also means that if we kind of account for sampling uncertainty, we have a lot of uncertainty, right? So we can think about this as helping us to bound-ish the possible correlation structure that we should be looking at. It also assumes that the fire risk is stationary, at least in the sample that we're estimating it on. That's impossible to tell of 22 years of data. But it does look like, if you just look at the time series, there's a cluster of really bad years from 2020 onwards. So probably the fire risk is not stationary, right, due to climate change and due to urbanization. Also assumes isotropy, so it assumes that correlation is not directional, and that's wrong because there's wind, right? But anyway, it's going to give us a sense roughly of what magnitudes of the correlations we might expect. And just to show you how accounting for correlation affects the carbon risk, in this left-hand panel here, we've got the case in which there's independence. And then for a single project, here's the kind of distribution of outcomes in the orange. And the carbon at risk is this really massive value of 566. But when you have 100 projects, the distribution squeezes in on itself, and the carbon at risk is lower. But in these other cases where we allow for some correlation between projects, right, there's less of a squeeze in the 1 versus 100 PDFs. And all I've done here is just plot the difference between the carbon at risk for the PDF with 100 projects and the PDF with just one project, and called that the diversification benefit. So this diversification benefit here is the difference in the carbon at risk between the K equals 100 and K equals 1 portfolios. And you can see really that obviously that decays very strongly with rho. And at the point, we know that obviously at the point when the correlation is 100%, then there's no benefits from diversification. So what did we kind of learn from this exercise? Well, we can say qualitatively, we can say quite a lot here, right? We can say carbon at risk varies a lot across regions due to the fundamental differences in fire risk and in regrowth. We know that diversification reduces carbon risk. Exactly how much it reduces it depends on whether you can find projects that are likely to have independent risks. And it also kind of suggests the biggest gains to diversification will be gain from spreading across regions where risks are less likely to be correlated. And it's really a call for kind of coordinated action on creating these types of portfolios, right? You can do a lot better if you can coordinate a portfolio across lots of different regions than you would if you put all of your forests in Cambridge. Any questions on that before I keep going?
So the one thing that we propose, and I sent you a link to a paper we did about this 2 years ago, is exactly when you have a loss of a buffer, essentially, you can basically put in more buffer. So your value at risk, your value risk can be stabilized by doing this. And in fact, what we do is, using our impermanence framework, is that we assume there's going to be a loss, and we make the credits less permanent. So if the loss actually doesn't happen, then we had some kind of extra buffer room. So we don't actually use a buffer, but we do, say, I'm going to adjust that in the future years.
Yeah.
So that even if there's a loss, we get this AR value to stabilize at any desired value.
Yeah.
By allocating future risks down the line. So we have an optimal allocation policy for future risk. It's too complicated to explain here, but it's in a paper we published a couple of years back.
Great. I'll definitely read that today. Okay, so that was an example in this kind of data-rich environment where we can get a sense of the empirical CDFs. But let's say we're in a data-poor environment, such as geological storage, and we don't really have observations on that. This is a very new technology. But we know that leakage is possible. So instead, we're going to use a model-based calculation.
Just geological storage, the throwing things underground.
Exactly, yeah. Okay. So people are doing this. I had a friend who was doing this session. Basically, they're flying these little planes around off the coasts of different places in the US and looking for places where there's like big caves underground. They could be actual caves, or they could just be areas where the rocks have different amount of porousness, basically, and trying to inject carbon into the earth. There's some crazy technology going on. I mean, people are also thinking about injecting it back into where people have done fracking as well, because we know that's a good place to store.
It's not that stupid as that the carbon dioxide reacts and forms calcium carbonate.
Yeah, so it's like potentially very long term, right? Because it kind of dissolves into the actual ground.
As long as no acid rain enters, it's okay. But acid rain makes it carbon dioxide again.
Yeah,
that's a leakage.
So there's obviously still some risk of leakage. So luckily, we can use. There are models that people have created to model the leakage. We're going to pull some of these off the shelf here and kind of model two different pathways. One in which there's a well-regulated offshore, one in which there's a poorly regulated onshore, try and get a sense of the CDS there. And when we kind of do that, we found that there's like an order of magnitude difference in the carbon at risk for different types of DACCS projects. So we looked at this kind of well-regulated offshore project, and this has got an extremely low carbon at risk. This is the carbon at risk here is kind of less than 1%. Whereas for an onshore unregulated project, the carbon at risk will be kind of 17, 18% in this simulation. And this is a very kind of important thing to note, really, because existing credit registries, at best, will do it by type of technology. And even within a technology type, right, we can have an order of magnitude difference in the risk due to the type of the way it's applied. So yeah, regulation, site selection, first order determinants of actual risk. So moving on to now portfolio design, rather than just looking at individual types of technologies. Well, the major use for carbon at risk would be at the portfolio level, right? People are considering, or corporations or national governments are not considering buying one project, one little parcel of land to put some trees on it. They're thinking of spending billions here, right, on mitigating their carbon emissions. And the idea is that by considering the carbon at risk, we could enable rational portfolio construction, ensuring that risks are kind of comparable and equitable. So to kind of illustrate this, we'll consider like an illustrative Bernoulli model where either a project fully delivers or fully fails. That's easy to relax. I think it gets the point across here. We're going to consider projects, a portfolio that's made up of DACCS and forest projects with some illustrative failure rates and illustrative project costs. And we're going to assume, some correlations between the projects. We're going to assume a very high correlation for the DACCS projects and a kind of moderate one for the forest projects, and show a bunch of sensitivities to that, basically. And we can kind of think about, a buyer or a kind of investor or a regulator who's interested in procuring as cheaply as possible, meeting some kind of CAR requirements. So they want to, in 95% of possible outcomes, they want to make sure that they get at least 30,000 tons of CO2 out of the atmosphere. But they would obviously like to do that as cheaply as possible. And you can think, you can just write that down as like a constrained optimization kind of thing if we know this relevant CDFs and the correlations between them, which we've assumed to do now. And there's some insight in thinking about the kind of conditions under which that equation is optimized. So you can write this as like a Lagrangian equation, and then think about what's the optimal structure of a portfolio that does the best job of possible of doing that. And the kind of key condition that will be satisfied for a portfolio that is optimum in this sense is that each dollar spent must deliver the same marginal contribution to improve the objective function. And what that means in this case is that each project's marginal value is kind of decomposed as the expected carbon that it brings, but there's some risk penalty. So you don't want to have a lot of risk. And the kind of key implication from writing it down like this is that if there is any correlation in the model, if there's any correlation between different projects in the same portfolio, then it's not the case that you'd always choose a portfolio that's made of all of one type of project, even if that project is cheaper per ton of carbon delivered on average. There's some gains to mixing because the risk penalty is a function of this, of the number of projects that you have now. So, okay, with that kind of intuition in mind, we can look at the kind of efficient portfolio design. So what I'm doing here, this is just purely illustrative, is taking 3 different portfolios that just meet the CAR requirements. So they deliver 30,000 tons of CO2 with 5% probability, but they only just meet that. So they're right on that border. And you can see here, this is 3 example portfolios. If we can zoom in, maybe I can. Yeah. So there's one which is all entirely made up of forest projects that has quite a wide CDF, right? There's a lot of carbon at risk, but it's relatively cheap. Whereas a all DACCS portfolio is much more expensive, but it has a much tighter CDF, and then some combination is in between those. And if you have what I'm calling as calibrated correlations here, then the forest project PDF just explodes because in the cases where one forest project burns, a lot of them burn, that really increases the carbon risk. And the costs, you probably, sorry, you can't see this here, but the costs increase for all of them. We can kind of think about the full set here of possible portfolios. So just think about every single portfolio, with 1, 2, 3, 4, 5 forests, and then 1, 2, 3, 4, 5 DACCS. Kind of visualize those. And each one of those different portfolios will have different properties, right? And here we're just kind of plotting the feasible space of options for places, for projects in terms of their expected carbon removed and the standard deviation of their carbon removed. And you can see, and then we're also coloring it by cost per ton. And you can see here that cheaper projects are generally the riskier ones. Cheaper portfolios are generally the riskier ones because the color gradient is kind of pushing outwards. But you can also see here that in the model in which we include these correlations, there's in general just more risk. So the whole distribution is pushed outwards. And I've just labeled those 3 portfolios that I showed in the previous slide here as well.
Again, using the correlation structure is time homogeneous.
Yeah. Yeah. Because yeah.
Okay. Because the thing is, as you have climate change, you have more correlation structure.
Yeah.
The larger scale forcing functions. So yes, the correlation will be there'll be more correlation with the far future than in the future. So there's a sort of a second order correlation structure effect as well.
That's it. Yeah. Yeah, that's a great point. I guess it's possible for us to try and bring that in.
Yeah, the other thing that's interesting is that your boundary points seem to have the centralized with all the corners having all the extremal values. So it looks like a index optimization problem to me.
Yeah, I think that's right.
Okay.
Yeah, this can be we can also think about the effective cost at those boundary points. So this is just like a heat map of the effective cost metric across all of the different projects. And when projects are independent, it's just better to use the one that's cheaper per unit delivered, which is the forests. But when when we include these correlations, that's not the case anymore. There's actually some benefits to mixing. Use that first order condition we saw before, and the kind of best portfolio mixes mixes projects, and now this one's a lot more realistic, this correlation structure. So kind of discussion. Under independence, you want to use the all forest portfolio. It's going to be cheaper and the risk diversifies away. So as you just get more projects, the risk just goes away, right? The distribution flattens in on itself. But under a kind of calibrated correlation structure, that's not the case anymore. Mixing is optimal. And the effective price frontier becomes U-shaped. So let's see if I can, oh yeah, maybe I said this, I accidentally skipped this slide. So this is kind of how risk relates to effective price on the frontier. So for the portfolios at that frontier. And the kind of the optimal mixing one is the lowest point of this curve. Okay, so policy implications. I'm going to finish a bit early, but it's okay. The first thing that we can look at is kind of comparing the buffer that we would get from using this empirical calibration to the buffers that people are using in practice in these registries. So if you're using a flat buffer like is used by the gold standard or some other carbon credit things, then you would be severely over buffered for example, an offshore DACCS project that's well regulated, but severely under buffered for forest fires, for forests in California. I think there's an important question about if this kind of proposal was ended up being used in policymaking or in companies, it'd be important to think about who's going to calculate it. There's obviously a moral hazard problem if project developers are the ones that calculate it, but they probably have the best understanding of the risks of their project. That's very analogous to the models that people are using in finance and banking, where I think up to the Basel Convention, whenever that was, 30-some years ago, VAR was usually calculated in-house from internal models, and people realize that's a problem, right? And you want to have either third parties calculate them or a very standardized methodology for how to calculate them that can be done by anyone. And we think there's some policy implications, buffer pool reform, I talked about that already. Also international cooperation on diversification. There's much more benefits from diversification if you can put them into different areas and insurance market entry. So yeah, there's some limitations here. We already kind of discussed this. This car represents threshold. It doesn't tell you something about how fat the tail is. This calibration was really just meant to be illustrative, and richer models can do a better job of it. But still, we think that it's a useful thing for policymakers. Can shift carbon removals from being in binary classifications to probabilistic risk-based management, which hopefully could enable risk calibrations, diversification, and good comparisons across different removal approaches. So that's it. Thanks.
So the correlations you were looking at, they're just sort of within that type of
Yeah.
Do you ever look at correlations across the different types, like sort of political or something like that might affect everything?
We do, and it's a complicated trade-off, isn't it? Because we can definitely, and we do, allow for that in the kind of sensitivity analysis, but to actually calibrate that really, that's the really is a big challenge, right? So you can do scenarios. You can say, look, in a scenario where the whole world goes to war, that's what's happening. But to assign a probability value to that just seems kind of impossible.
Right.
But it's a great point, yeah.
But I guess it's just, it's the sensitivity. Like, how much does it? Like, if you introduce a little bit of correlation, then does that to things like?
I guess if it's just like a flat correlation that applies to everything, it won't change the ordering of the different portfolios. So whilst it changes how much is like the kind of absolute level, still you've got the same optimal portfolio and things like that. Where it gets really messy, right, is if it changes the ordering as well, which is definitely possible. So yeah. We're trying to do it now, like for like a big portfolio of different types, so like 5 different types of projects, and trying to empirically calibrate like the full variance covariance matrix for those different projects using real world data where possible. Yeah, I guess this is just going to be like a proof of concept.
You mentioned that currently we remove 2 gigatons of carbon per year and you get to 10. What is it the current to, what is the breakdown of? Is that all from forests?
It's pretty much all from forests. It's like 90% from forests or
Okay.
95% from forests.
Okay.
And that's why there's so much investment needed, is because the forest bit, well, that doesn't need that much investment. We know how to plant trees, right? But in order to scale to that level of carbon removals, given urbanization and land use changes that are almost certainly going to happen as well, we have to have these novel carbon removal technologies, like pumping it into the ground or doing other crazy stuff like sending it to Mars. Obviously not that, but you know what I mean.
The creative one. What do you think is feasible with just trees? Like, is there found?
I mean, it's just going to be unbelievably expensive, right? To do. There's some cost trade-off where it's possible to plant trees in the center of Los Angeles, right? But that would be infinitely expensive, right? So I think it seems to be the case that the optimal way to get to 7 to 9 gigatons includes quite a lot of these novel technologies, because the costs of planting trees in places where you'd have to plant them to get that levels of removals is just not feasible.
So with like feasible places, how much do you think?
I think that report that I cited in the first slide, I think that was saying that we need to have about 60% of the growth from these novel technologies.
Yeah. So that'd be like 2 gigatons-ish from trees.
So that's a lot.
Yeah.
And that 2 gigatons, how much that you mentioned the additionality thing, like how much can we sort of trust that in a sense, right? Like how much are people like if that would that happen anyways?
There are studies that have been there are some studies on this, and the studies that I've seen at least are all pretty pessimistic. So yeah, that's the best guess. That's in the reports, but who knows? Yeah.
Another question. I think it was towards the beginning. So you want to buy extra things to cover the risk, so let's say like 95%. Do you also consider the risk on the thing you're buying as?
Oh yeah, we do. Yeah. Okay. Yeah, that's a good point.
Yeah. So you have to.
It's like
account for it.
Yeah. Okay. But I guess it has some limit, right?
Right. It gets smaller and smaller.
Yeah. It's a really important point.
Okay. That's good.
Cool. Thanks, Simon.
Thank you.